So, in this video, today we're going to look at energetics calculations. So, energetics, we're talking about delta H, Hess cycles, and all the different energy change type things we could calculate using specific heat capacity, all those things. So before we get to calculations, we're going to talk about definitions. And you might be thinking that these are completely separate things, but if you can't remember the definitions clearly, you won't be able to write the equations clearly when you're not given them, and therefore you might come unstuck. Also, by remembering the definitions, you're just going to work out what they have in common, and one of the things you might see from all four of these definitions is they have 1 mole in common, but because our energy changes are measured in kilojoules per mole. So the top two I've grouped together because they are energy changes for whole reactions. So the first one is enthalpy of formation, the second is combustion. They both have 1 mole in common, and the top one is formation, the second one is combustion, but they are both under standard conditions. And that's something that most enthalpy changes also have in common. You may feel like you have to write standard states and standard conditions for the top one. That's fine. Every A-level board has very slight different variations of these. But what they all have in common, as I said, is the 1 mole. They're defining what the reaction is, so formed from its elements, or combusts completely, or combusts in excess oxygen, whatever it is that you have to remember. One thing to note is that they both start with the words enthalpy change and not energy required. So both of these enthalpy changes are in fact exothermic nearly all the time. So the second one, combustion, is always exothermic. Formation is almost always exothermic. And that makes sense if you think about the difference between elements and compounds, that most of the time we find elements in compounds. We don't find them as unreacted elements. That is telling us compounds are more stable than elements, which means that generally they give out energy when we form compounds. There are a few enthalpy change of formation that are not negative. They are for particularly unstable compounds, like hydrogen peroxide, for example. Second two, similarities and differences. So this is bond enthalpy and ionization enthalpy. So these are not full chemical reactions. These are kind of small individual processes that could happen, breaking a bond or removing an electron. So how are they the same and how are they different? Well, they now say energy required, and that is because we are either breaking a bond or removing electrons, so it's endothermic, overcoming attraction. Still 1 mole. Instead of standard states, we're now having gas states. And the reason we're having gas states is if you think about the bond enthalpy idea, and say you have iodine. So iodine is molecular, it goes around as I2. Iodine is a solid at room temperature. So if I wanted to measure the enthalpy that required to break the covalent bond between iodine atoms, I would first need to heat up that solid and separate the molecules. So otherwise I'm not getting the individual energy required to break the bonds, I'm getting a combination of energy required to turn iodine into a gas and then the energy required to break the bond. So we start as a gas. The same for ionization energy. If you think about removing electrons, sodium is normally a solid and its outer electron is delocalized in that lattice. Okay, all these calculations link together. This is a common thing that A-level students do, and GCSE students all the way through, which is to try and learn each part of a topic or each topic on its own, kind of in isolation, without looking at the links between it. So a typical A-level energetics topic will cover enthalpy profile diagrams, so the little up and down diagram on the left, which you probably did at GCSE as well. They will cover bond enthalpy calculations at the top there, And most of us will just rote learn bonds broken minus bonds made and not really think about the origins of that calculation. Bottom left, we've got experimental calculations where we're measuring the change in temperature and using specific heat capacity. And then the main part here is the Hess cycle, which is the main bit that people struggle with because it's new to A level, whereas most of the other things people have covered before. So let's have a look at how these things can link together because they may not be separate to each other in a question. So the bonds broken part. Let's look at the enthalpy level diagram. Well, we could label that activation energy, but it is essentially the energy required to break the bonds. So we're going from the reactants to the highest point in the diagram. The bonds made is represented by the arrow going down. So I can see in this reaction it's exothermic because there's more energy given out when bonds are made than is taken in when bonds are broken. And that means my delta H has a negative sign, and that's why the arrow goes downwards in the diagram. So in reality, bond enthalpies are always positive, endothermic, but because we're going from the atoms down to the products, that's why we would say minus bonds made, because we are switching the sign and saying that when you make a bond, it's given out. Same idea, if we took a combustion reaction, we could work out the enthalpy change using that bonds broken, bonds made, but we could also put that in a Hess cycle. So what we're saying here is that if you were to break the carbon, hydrogen and oxygen bonds on the left-hand side, your products would be what we've got down the bottom here. Single atoms of carbon, hydrogen and oxygen, because I've broken them all up. And on the right-hand side, if I broke all of those bonds in the OH and the CO bonds, I would also end up with the same thing. So you can see that actually all we're doing is just linking to energy processes to find the energy change at the top. So we're just using Hess's law when we do bonds broken minus bonds made. We do minus because that arrow on the right, we have to switch the sign. So what about the calculations for enthalpy change? Well, I could measure the enthalpy change practically using this whole Q equals mc delta T using specific heat capacity and heating water. So there is no reason that that could not come up in a question about Hess cycles or in a question to indirectly work out a single bond enthalpy. So the important thing is that we're not necessarily always going to be working out the same thing. We might have to just work out one of the bonds. Hess cycles. Why do the arrows go up? Why do the arrows go down? I've heard many students say that they can't remember which way to draw the arrows in a Hess cycle. This worries me because it's not something you should be remembering, it's something that you should work out by thinking about what the reaction is. So take a moment and think. Nobody has ever told me that they don't know how to draw the arrow at the top. And what I mean by that is that arrow going from C2H4 plus H2O to C2H5OH. Everybody knows that that arrow goes from left to right. And that is because that is an irreversible reaction and that is the direction from reactants to products. So that's how you know which way the arrows go in a Hess cycle. So I could use combustion enthalpies to work out the reaction at the top, because if I combust ethene on the left-hand side, I will make CO2 and H2O, and if I combust ethanol, I will also make CO2 and H2O. That's why my arrows go down, because CO2 and H2O are the products of the reaction of combustion. I haven't written the oxygen in there. We don't normally write the oxygen. I'm going to put it in there because it's going to be useful later when we look at a more complicated example. Okay, looking at the bottom example, using delta H of formation, which way the arrows go in that case. So, thinking of our definition, elements form compounds. You start with elements, you end with compounds. So once I've got elements at the bottom, that's what I'm going to do. I'm going to react them to form the compounds. So that's why in this example, the arrows go upwards. So don't try to rote learn it. Just think of them as reaction arrows. That's all they are. They've just been written sideways on instead of going straight across the page. Okay. Once you've decided which way your arrows go, based on the reactions you've been given, your next challenge in a Hess cycle is working out one of the enthalpy changes from the other. And there's really only three main possibilities. So on the left, you can have both arrows going down. The middle one, you have both arrows going up. The one on the right, we have an arrow going down and an arrow going up. So what they also all have in common is that you can start from one point in a Hess cycle and you can travel along two arrows in the direction of the reaction, and you can reach the final product either by going via two reactions or via one. So looking at the one on the left, if I start at point A, I can react A to form B, and then I can react B to form X. Or I can go straight from A to X, and the total enthalpy change should be the same. So I'm going to use that information to write an equation that links the three enthalpy changes. So therefore, if I add up the enthalpy change for delta H plus the enthalpy change for number 2, it equals the enthalpy change for number 1. In the middle example, I can't start at A because the arrows don't go the same way, but I can start at Y and go to A and then go to B. And that means that number 1 plus delta H equals the enthalpy change for reaction 2. And then the final one on the right-hand side, this is a particularly nice example that doesn't come up very often because it results in the delta H being the subject of the equation. Basically, I can go from A to Z to B, or I can go straight from A to B. So why are we writing it like this and not just going, oh, you switch the arrows round? Well, switching the arrows round works sometimes, most of the time, if you remember why you're switching the arrow round. Problem with switching the arrows round is what happens when you have more than two arrows or when it just looks slightly different. So by doing this, I'm not switching any signs of anything. I'm simply rearranging maths and I'm keeping the numbers as they are. So if you're lucky, you may have seen a diagram like the one on the right, which is Bourne Harbour. The one on the left is going to come up when you look at ionic substances dissolving. So this method, following arrows in one direction, clockwise and anti-clockwise, works for these sorts of diagrams as well. These are just Hess cycles arranged in energy levels. So if I add 1 and 2, it gives me the same enthalpy change as the overall reaction for energy level 3. Notice that this also looks like our standard reaction profile, bonds broken and bonds made. On the right hand side, there's a lot more energy changes, and in a Hess cycle you could have as many as 7. But the same idea goes, I can still start, follow 5 of those enthalpy changes round, and all of those enthalpy changes added together equals the enthalpy change for number 6. Why that's important is it means I can find enthalpy change number 4, number 2, I can rearrange it to find anything. Whereas if I try to rote learn switching one arrow round, it becomes more difficult to rearrange it when you get something else that is the subject of the equation. So think about the direction of arrows and then simply find one point where you can either go clockwise or anti-clockwise and get the same energy change. Okay, a tough example or an unfamiliar example. Displacement reactions of metals. I'm given 2 enthalpy changes and asked to work out the third. They're not combustions, they're not formations. So before we panic, what we're going to do We could just say, oh, we've got two numbers, I'll try and rearrange them, but unfortunately it says make your working clear. So it probably requires a Hess cycle because I'm linking one reaction with two others. So before we panic, we're going to think of an example that we are much more familiar with to show how it can be applied to this situation. We're going to look at using combustion. This was an example I had earlier, which was ethane plus water making ethanol. So ethane reacts with oxygen to make carbon dioxide and water. Ethanol also reacts with oxygen to make carbon dioxide and water. And it's the products in common, which is why we can link them in a Hess cycle. There is a point we can go through for both reactions. So we can use those two reactions above to work out the reaction of ethane and steam, which is very hard to work out directly because it's done at high pressure and high temperature with a catalyst. So it's very difficult to measure that enthalpy change. So we can measure the top two because they're combustions. Those are easy to measure. So what do we do in a combustion enthalpy? Well, C2H4 is one of the reactants. I've just underlined it to make it clear, and it's a reactant at the top. So both of them have been used in the equation at the top. Oxygen is in common for both of those. I've added oxygen to both ethene and I've added oxygen to ethanol. So you're looking for, in a Hess cycle, what have I done that's in common to both sides? When I add oxygen to both of those, I make the same products, carbon dioxide and water. So I've done the balancing for ethanol. So when I add 3 moles of oxygen to ethanol, my arrow goes down because those are the products, 2 moles of carbon dioxide, 3 moles of water. I've ticked off what I've used in the equations at the top. When I add 3 moles of oxygen to ethene, I make the same thing in terms of carbon dioxide, 2 moles of carbon dioxide. Now I make 2 moles of water, but that's okay because there's already a mole of water on the left-hand side there. There's no energy change going from 1 mole of water to another mole of water. So 2 moles of water are made from the combustion. 1 mole of water was already there. So that kind of cancels out. It doesn't matter. It's the same as the oxygen. So if I look at the top reaction, I'm actually trying to measure the enthalpy change or determine the enthalpy change going from C2H4 plus H2O to make C2H5OH. There's 3 moles of oxygen on each side because that's what I added to balance the combustion equation, but that's okay. It doesn't make any impact on the top equation because it cancels out. 3 moles of oxygen on both sides. Normally I would just cross them out. So how does this apply to this less familiar example of metals displacement reactions, which you probably haven't done since GCSE much? So I've got the reaction I want to find. I'm always going to try and put the unknown enthalpy change at the top of the Hess cycle. Just makes it easier to rearrange it and visualize what's happening. So, like we did with the combustion, I'm just going to look at what I've already used and tick it off. So I've already used zinc sulfate, magnesium sulfate, zinc and magnesium. And I've got copper sulfate and copper as kind of leftovers, which have not been put anywhere in the Hess cycle. So they need to be involved somewhere. So copper sulfate is a reactant and copper is a product for these reactions. And like the oxygen situation, I don't want to be putting copper sulfate down the bottom because copper sulfate is a reactant. So it's going to go at the top. The product that they have in common, this is like the CO2 and the H2O, is copper. So copper is the one thing that both of these reactions make. Now I need to work out what else they make, because clearly they can't just make copper. So if I add magnesium to copper sulfate, I'm now going to add my copper sulfate at the top left, then my products are copper, I've already got that. My arrow goes down because that's a product. And then the other product that has not been accounted for is magnesium sulfate. So I'm going to put that at the bottom of my Hess cycle as well. So far, left going downwards, I've got copper sulfate plus magnesium. We'll worry about the zinc sulfate in a minute. So looking at the right-hand side, I've got zinc, and zinc reacts with copper sulfate too. So zinc and magnesium are both reactive metals. And when zinc reacts with copper sulfate, it obviously also makes copper because it displaces copper, and it makes zinc sulfate as a product because the zinc needs to go somewhere. The zinc loses electrons and becomes oxidized. So now hopefully it's starting to become a little bit clearer. When you add magnesium and copper sulfate, you make copper and magnesium sulfate. The zinc sulfate was already there on the left, so it's like the water in the previous example in that we don't need to measure the enthalpy change of it, because there's no enthalpy change going from zinc sulfate to zinc sulfate. When I add zinc and copper sulfate, I'm going to make my products are going to be copper and zinc sulfate, and again the magnesium sulfate is already there on the right hand side, so there's no energy change getting in the way of that calculation. So now I just need to put the corresponding enthalpy changes next to those reactions, making sure I get it the right way round. So zinc was the minus 219, magnesium was the minus 530. Delta H is what I'm trying to find. Using the arrow method, delta H plus minus 219, I didn't bother putting the plus in, equals minus 530. So I've done no switching of signs right now. I am going to move the 219 to the other side to make delta H the subject. That's what we mean when we say change the sign of the arrow going the other way. We're just rearranging an equation. So I get my final answer as minus 311 kilojoules per mole. I'd look at it now and make sure that it makes sense. So always when you're getting to the end of a Hess cycle or another enthalpy change calculation, always going to make sure that it makes sense in the context of the information given. Well, the other two delta H's were negative, and they were displacements of metals, so I expect this to be negative too, even if I don't know whether it's exo or endothermic. It's in between the two values, that's because it's sort of in between the difference in reactivity, and therefore it makes sense. So if I was going to get a positive value, that would be crazy, especially if it was a large number. So always sense checking. When you get combustion, combustion should be very large and negative. When you get formation, it's usually negative, but it's not so large. And reactions can also be anywhere, of course. Bond enthalpies should be positive because their energy's in. So hopefully that was very helpful. You're now going to go and have a go at the enthalpy change questions if you haven't done so already, and I'll give you the answers to those enthalpy change questions tomorrow when you've had a good practice.